Here we go again. This is the Wednesday morning poster session. We'll try to find some cool papers. It's just as big as all the other poster sessions. Goes from all the way back there to all of this hall here. Insane. Hi.
Hi.
Hey.
Big fan. Nice meeting you.
I'm recording a bit. Is that okay?
Yeah, sure.
Can you tell us about bifurcations in RNN trading?
In RNN trading, okay, now I'm getting nervous. Like general rundown, like we were interested in finding how RNN trading works and why we have sometimes problems.
Yeah.
The way we did that is, so for example, first we use like normal rarely activated RNNs.
Yeah.
And the reason we do that is because we're analytically tractable. So we actually have a closed form solution for fixed points and K cycles. And that we can calculate. Like it's just this equation. And the bifurcation is just like a quantitative change in your dynamical behavior of your system. So changing from fixed point behavior to cyclic behavior.
So what kind of stuff are you training here? Do you somehow assume an infinite length sequence of inputs, or how can you talk about fixed points?
For the benchmarks, we use like brands like Lorentz system and stuff like that. And for example, here we have like empirical data from membrane voltage tracers of the cells. So we got a recording and we trained on that.
Yeah.
And what we found is that during training, like you have like this big jumps in the loss. And we use our algorithm to analyze what kind of dynamics are going on.
Okay.
And what we had here was like we have a fixed point after the jump. So you see before the jump we have a fairly well-trained system. It's not perfect, but you see it's like close to what we actually want. And then suddenly at this point we go to basically infinity.
Yeah.
And also we have like divergent behavior.
Can you tell us a bit? So what's the data exactly here? That's a time series.
Exactly, it's a time series of membrane voltage. So we recorded like, not we, but like the people we got the data from, they recorded on a cell, they reported the membrane voltage over time. So you just took membrane voltage.
And do you think the problem has to do with the fact that there's these spikes in the data and so on, and these might be discontinuities?
In general, you always see like this kind of behavior if you train RNNs. Like you always have like these jumps in the loss because of those types of bifurcation.
And even if I train like a language RNN or something,
language RNN,
like an RNN on I don't know, like some sentence of language.
Yeah, I would say like. In general, what we observe is that always it looks something like this usually. We have always those jumps in the loss. It's not always that big, like that is like exceptional, but usually always have like wiggly behavior in your loss. You're never like completely straight. And it's just because your loss landscape is like very crooked at some point. You have like those jumps in the loss landscape.
Yeah.
What we wanted to do is we wanted to calculate all those dynamical objects. We want to find the fixed points. We want to calculate the K cycles of those objects. We can relate that to the bifurcation curves. Like for example, this is a 2D example. This is like analytically calculated bifurcation curves. So we know, for example, here this SRL, this is the region where we have a stable 2 cycle.
Yeah.
This would be where we have a stable 3 cycle, and here we have like multi-stability. So we have both existing at the same time. And this is all analytically calculated. And now we...
And to give us a background, the 2 cycle and the 3 cycle are what?
2 cycle and 3 cycle would just be like you have here. Yeah, you have like the time series here. So 2 cycle would be the red one where you just jump between 2 states.
Yeah.
And the 3 cycle would be jumping between 3 states.
Okay. And those states are weights, like you jump from one weight configuration to another?
No, you have one fixed weight configuration. So the time series produced by your model, like the states, you jump between the states.
I see, yeah.
And we try to reproduce that with like our approach, which is semi-analytical, where we calculate just like on a grid here, we calculate those dynamical objects, and we actually find all of those bifurcation curves.
Okay.
This was basically a validation for our code to see that we actually work. The problem with like this analytical approach is you have an equation like for a fixed point in every single of those linear regions given by your ReLU activation function. And in general, you would need to solve for every single of those linear regions, which is going to be tedious if you have like a 100-dimensional RNN. Like it scales with 2 to the power of your dimension, like the quadrats. So the idea we came up with was this heuristic where you like initialize in one random quadrant, and then you calculate your equation. Like the definition would be now, if the solution lies in the same quadrant, then you have a real fixed point, so you will just stay there. If your solution lies in another quadrant, then it will be a virtual fixed point. So if you are here, you will feel attracted to that, but as soon as you cross over, it doesn't exist anymore. So yeah. The idea would be now to reinitialize the algorithm, the calculation here, in the quadrant of that virtual fixed point.
So wherever you go, you reinitialize.
Exactly. Yeah. And that works surprisingly well. So here is like a scaling example. The black one would be like just if you would randomly pick a quadrant and calculate it there, it would scale like that. And those are like how our algorithm scales. So it depends a lot on like the eigenvectors on the matrix norms.
Yeah.
But in general, it always scales better than by just randomly looking at those quadrants.
Yeah.
And then we use that algorithm to actually calculate bifurcation curves in, like, for example, in this toy example. And you see all those, like this is the loss gradient, and this is the loss, the actual loss. And you see that all the jumps in the loss are actually aligned by bifurcation curves.
Yeah.
Which means whenever you have a jump in the loss, it's probably caused by a bifurcation.
Yeah.
But not every bifurcation causes like a loss channel. Always depends. And like coming from that toy example, we did that on the real data. And what we found was we find these types of bifurcations in that training as well. The cool thing is we cannot only analyze the training process, but we can analyze the fully trained system. So our goal is not just to do good prediction, but we do dynamical systems reconstruction.
Yeah.
So we actually want the full dynamical system and not just good prediction. And once we're trained here, we can calculate all the dynamical objects. Like what we have here is, for example, a stable 39 cycle, which would describe this cycle you can see here.
Okay.
But that's not everything we found. We also found like a stable fixed point that exists at the same time. And then we have this unstable 9 cycle, and we have an unstable 39 cycle. And the question is now, like, if we have a real proxy for the biological system, this should have a meaning. Like, this fixed point would mean something.
Yeah.
So this is what we're going to work on, like, in the future, like relating that to actual biological things. Coming back to the training, what we found is that like a form of teacher forcing, like generalized teacher forcing, that was proposed at ICML this year, actually helps a lot in getting rid of those crazy jumps.
Okay.
Like this degenerate transcritical bifurcation that causes that jump is not possible if you choose your factor alpha here correctly. So you smooth your loss landscape and you make RNN training easier, like and much faster.
Okay. So you found why this method helps.
Exactly.
Okay.
We found out why this actually works.
Okay. Pretty cool. Very nice. The fixed points that you found, you said, they must be explained somehow by something real. The 39
That's what we would think,
39 cycle 6 point fixed point would be the spikes. Do you have a clue what the 9 cycle would be? Okay.
So it might still be just an artifact from the training.
Yeah.
So this is something we have to figure out. And you have to find metrics to say, okay, is this now fully trained? Are we really, like, do we actually have a proxy for the system?
Yeah.
But yeah, that's like the work in progress, what we actually want to do now. Like sometimes you just get artifacts during the training process, and sometimes it might have a meaning. But yeah, that's something we want to figure out now.
Very cool.
Thank you so much.
Thanks a lot.
Thank you, man.
Nice to meet you.
Nice to meet you. Very gradient iterative.
Well, let's focus on this one. Tell me about it.
LEDITS
This is Paulie. He's very cool. Follow him on Twitter.
LEDITS++ is a technique that leverages the semantic guidance, but for editing real images, while semantic guidance edits images on the latent space of stable diffusion. LEDITS++ edits real images, so we first do inversion. So we take an image and we invert it back into the latent space, but we do DPM solver ++ inversion, which is an innovation on this paper because it hasn't been done before. And basically you can do inversion in as little as 50 steps, maybe even less.
What kind of models do you invert?
Basically, you can do any pre-trained text-to-image diffusion model. So here we do Stable Diffusion 1.52 or XL. And essentially, it's the combination between the inversion, then applying the semantic guidance technique. So we can guide, for example, Jan LeCun to be George Clooney with sunglasses. So you do 2 edits at once. It's all inference time. You don't need pre-training. You don't need further fine-tuning. And another innovation from that's Y++ from the technique is that we do semantic grounding. So these masks are already free on the Stable Diffusion UNet, so both the UNet masks and also the noise masks. And when you use them, you essentially ground your edits into the model.
What does it mean using them? Do I have to do something, or?
So basically this means that, so here for example, no masking and no pipelining model, so you don't need the segment, anything connected.
Yeah.
Basically you just type cherry blossom and the model finds that already it has the knowledge that there is a tree here, so it replaces the tree with the cherry blossom without you having to point where the cherry blossom is. And also, you remove the yellow car. So this is the original image, right? The car was yellow. So basically, we remove yellow car, we add green convertible, and we add cherry blossom. And basically, for free, without masking, without saying where, the model semantically finds the cherry blossom. It removes the yellow car and it adds a green convertible. But you see, it kept a lot of the structure. You kept the background. And this
but it does the mask after it did this, or it uses the mask to do this?
It uses the mask to do
so
it.
You type, because there is no cherry blossom here, right?
Yeah.
So you say plus cherry blossom, it would kind of semantically find that cherry blossom is a tree, and therefore the tree is here.
Yeah.
Okay. And you could use that. So this is just a reconstruction. So you don't. Where do you start? You start from reconstruction.
Yeah.
When you want to do when you want to edit a real image, you first have to find the noise from which you start to actually edit the image.
Yeah.
And that's why you have to reconstruct the. Or that's why you have to. Yeah, I think reconstruction is maybe not the right word here, but anyways.
That's a word.
So you start from this image, you invert it. And then when you want to do the textual editing, as Polly was saying, the word is grounded in the image. So the model has a knowledge on where cherry blossom is relevant in the image. And so it limits the editing already to the based on the model's knowledge to the relevant image region.
Okay.
That's quite cool because we're really focusing on the relevant parts and get masks for free.
Yeah.
Yeah. So basically, this for example is what you would do if you just do the inversion reconstruction and the textual editing without the mask grounding.
Yeah.
You see that it actually does it, right? You do add the cherry blossom and you kind of change the car, but like it looks a bit like the car light is it has a bit of the cherry blossom vibe, like with the pink, and the car kind of changed quite a lot.
Yeah.
So with the grounding, by using the knowledge of the model of the masks, and it's an averaging of both the UNet and the noise, it manages to actually do a way better edit.
Nice. Very cool. Very cool. And this is all for free?
All for free, all inference time. The only
it's a great price.
tricky thing is that you have to do inversion.
Yeah.
So like the first step, you have to like run the 50 steps of inversion to then. But then once the one image is inverted, like once you have all the latents, you can reuse. You don't need to do inversion every time. You do it once, and then inference is free.
Okay. The inversion takes roughly a second, so it's still quite quick.
Yeah.
But and it's also reconstruction error free, so it's like perfect inversion and fast inversion. So it's not really a downside, I think.
Yeah.
Very cool.
Then you
Excellent. Thank you.
Thank you. Thank you.
Thanks.
Enjoy the rest.
I read a bunch of question answers.
Is it okay if I record a bit? Or?
Feel free.
Okay,
I
cool.
will try my best.
Very cool, thank you.
So this work we basically investigate is it possible for the model to be performed without any fixed token embedding. So fixed token embedding is basically has been here since first Word language. So it's like mapping from token to fixed vectors. If you don't have this, that means the token no longer have this identity, being in context independent identity. You only have token meaning by how it acts in the context. So Lexinvariance is basically like this idea of like these three phrases are equivalent because it's only different up to lexical mapping. So letter E here, you can obviously see as A because E appears here and here and here and here, and the same thing as A. Yeah. So this is a Lexinvariance. So we basically show that this Lexinvariant language model can converge to standard language model in terms of next token prediction. which is very surprising because you have this property. And we show empirically also does the same thing. So Lexinvariant language model, we kind of constructed by replacing fixed token embedding in transformer with random Gaussian embedding. So basically, this the E here will receive the same token embedding, the same random Gaussian vector token embedding, the same replacing the sequence, but across different sequences, the same E will have different token embedding.
Could you kind of intuitively explain how the random Gaussian encoding works?
Yeah, so basically, as I was saying, basically, the letter E here, right? It receives just literally randomly sample a Gaussian vector for it, and then the same E here will have the same random Gaussian embedding at every places. And so similarly, C has the same random Gaussian embedding, and K has the same random Gaussian embedding.
Oh, the embedding is the first occurrence of that character, whichever mapping it is, and then the remaining occurrence.
You can figure it that way. Yeah.
Oh, okay.
But across different sequences, your same letter will have a different Gaussian embedding, so that you force it to have Lexinvariant property.
What do you predict then? Do you predict into a standard vocabulary?
No, you predict it still in Gaussian embedding, the random Gaussian embedding. So let's say.
But what if you don't have that particular letter that you want?
Oh, you don't have it yet. That's a good question. So then you cannot really predict it out.
Yeah.
So that one will just be you can't do anything there.
Okay.
Does that mean you have to use something like
No, you can do any tokenization. You just need to replace whatever token to random Gaussian.
Right. But I thought the point was if it's not already in the maybe I misunderstood the question, but so right, if it's all random, and let's say you have, will this be able to predict a letter that's not there?
No, that's the same.
Right.
You won't be able to.
Or a token that's not there, right? So if you tokenize...
So if your token, if your vocabulary is really large, if you go beyond character and you do
Yeah, that's why it needs a really large context lens.
And all the vocabulary is in the input, right? If you change the input, then it's not.
So usually, and this is perplexity on language modeling on an RNN.
No, this is a theoretical proof.
Okay.
This is nothing to do with this. This is all transformer. So all the empirical stuff of this decoder only transformer.
Okay. And perplexity is usually measured sort of on the log scale. So this difference here would actually be quite big, no?
Yeah, this difference is decently big.
Yeah. So it kind of derives all it does from just kind of how tokens relate to each other?
Yeah, exactly.
Okay.
Yeah, so that's the key. And we also show that Lexinvariant model performs in-context deciphering with uncertainty. And so basically because it sees all the substitution cipher as the same sequence, so it literally performs implicitly this in-context deciphering. We can probe out the cipher key by just training a linear layer on top of the frozen random models.
Yeah.
And we finally show that Lexinvariant model is substituted better at the symbol manipulation task. So symbol manipulation task, we have two tasks. So one is a lookup table. So you have a lookup table and you predict the next token by looking up what's token back to.
Yeah.
And the other one is permutation. So you permute the sequence the same way as the demonstration. And we show that we can achieve 4x improvements on this.
But these are very constructed to favor you a little bit. Okay. Very cool. So does it mean that a lot of language is just sort of how things relate to each other and not just the absolute words?
Yeah.
Okay. It's very interesting. Very cool. Thank you. Yannick, nice to meet you. Transformers implement preconditioned gradient descent for that's very cool. So you figure that if in-context learning happens, what's actually happening is some sort of gradient descent.
We had that discussion. Idea is that if you want to solve this square with the transformer and you train it on the random data generated to solve this square, the network when you increase the number of layers, the network across the layers is implementing some algorithm which is a preconditioned
preconditioned gradient descent. This how we can define this, characterize it. You study the structure of the objective that is used to optimize the parameters.
Yeah.
You characterize what is the optimal parameter.
Yeah.
You plug in it there and see what happens.
Yeah.
And then you can interpret it as an algorithm.
Yeah.
Algorithm.
So how do you get a transformer to even tackle least squares? What do you do as the inputs and outputs?
Sure. The inputs are x, I, y, I.
Yeah.
Context example of least square. We encode one example of least square in the prompt.
So all of this is in context, and then this is the sort of next token you predict.
Exactly.
Okay. And you solve least. That's very cool. And then you train on a lot of these examples.
Exactly.
Okay. I would expect that transformer to just kind of memorize a lot of stuff. It seems like you're more saying you're actually doing an algorithm internally.
That doesn't mean.
Okay, that's very interesting.
So you can there is a memorization, as you said. That's correct.
Yeah.
The memorization is in the. So suppose that you have a data distribution that is Gaussian with some covariance.
Yeah.
Then the optimal parameters that you find depends on the sigma matrix, depends on the spectrum of the sigma matrix.
Yeah.
So there is a memorization.
Exactly like
the algorithm adapts to the data.
Yeah.
It becomes preconditioned, but it's not that different from training.
Okay. The memorization accounts for the preconditioning. Nice.
It's actually the way.
Very cool. And then, how do you make this actually how do you interpret it into an algorithm then? So once you have the preconditioning matrix.
It's a very good question, because we are updating the data distribution, not the. So we don't have parameters of least square getting updated. So the way that you can connect these two is that you can prove that this yn plus 1 has different instances across the layers. It's getting updated across the layers. When you pass the data across the layer, this y at the beginning it was 0, it becomes something and something at the end.
Also, you track how it evolves over the layers, and that's kind of the algorithm then.
This would be equivalent of projecting this gradient step on the xn plus 1.
Okay.
So this is the way that is literally.
You show this theoretically?
So theoretically, for single layer, you can say global optimum is exactly this algorithm. You can say what is the preconditioning matrix. For multi-layer, the result is weaker. We prove there is a stationary point that is gradient. We couldn't say it's global minimum, it's local minimum, it's just a station.
Okay. And then you try it out in practice?
In practice, we optimize it, and we found that it's even for multi-layer, we are converging to the same structure that we characterize, to the same, let's say, stationary point.
Very cool. Very awesome. What's the implication? Thanks for that explanation. Hey, what's up?
Hello. Nice meeting you. Yannick, I've seen your videos.
Is it okay if I record a bit?
Of course. I'd like to give you the speed if you'd like to hear it.
I would love to.
Amazing. Yeah. So basically, the motivation of doing this work was that we saw the very great potential of human preferences in language domain.
Yeah.
You obviously know it from Open Assistant, ChatGPT, etc. And we wanted selfishly to do it in text image generation. But the problem was that there was no large publicly available data set to do it with. So we decided that we'll collect one and open source it.
Mm-hmm.
So we did it by creating a website that enables users to generate images from text for free. That's actually like screenshots from the website.
Mm-hmm.
So the users were able to enter the website, write their own inventive prompts, generate images, and to see the next image, they needed to choose which image they prefer.
Yeah.
This allowed us to collect a dataset that contains more than 1 million examples of human preferences in text to image.
Yeah.
In which each image contains a prompt, 2 images, and a preference for which image is preferred.
Yeah.
Or if
Very
there
cool.
is no hard preference.
Yeah.
And you can take a look at this data. It's very, very, very different than the data that you'd see on MS Coco, for example. The images are much more diverse, much more interesting, and the prompts can be funny, scary, and not boring like MS Coco. And cool. So this dataset is great, but we also wanted to show that we can actually utilize it.
Yeah.
So what we've done is we trained a scoring function that we call Pick-Score. It's CLIP-based scoring function that is supposed to estimate the level of satisfaction of the user from the image given the prompt.
So as a reward model.
Exactly. We wanted to train a reward model. Put it simply. And the input is a prompt and an image, and the output is a score. And we used, to put it bluntly, we used an analogous subjective data of Instruct GPT. And then when we measured Pick-Score's ability to predict human preferences, we showed that surprisingly, it's not only better than existing scoring functions, it's even better than human experts. And that like a lot of people say but wait, that doesn't make sense. This dataset was created by humans, so I can be superhuman. And the core distinction is that the user that created that example has much more information than the crowd worker. The crowd worker can only get as input like the prompt and the images. They don't know what the user had in mind, what they envisioned, and the model needs to pick up on that, or the crowd worker. So I think that it shows an important insight also, this fact that you also probably saw in Open Assistant, that real users can provide you with much higher quality data than crowd workers.
Your incentive was this is a free image generation.
The incentive for the users was free, very high quality image generation, and our incentive was we want to open source stuff for the community and to push research. So using the scoring function, we showed that we can perform much better model evaluation than the one that can be done with FID, which is the standard metric for evaluating text-to-image models. But it shouldn't be, because it's a very bad metric that doesn't even consider the prompts. So Pick-Score correlates better in model evaluation, better than FID on MS Coco, and better than other scoring functions on.
This is a small difference. No,
this is minus. FID shows negative correlation.
Well, but then I could still predict. Just by taking the negative. But still,
it's Actually, I agree, but yeah.
Well,
that's a fact.
If it's so negative that it's negatively correlated.
That's a fact. But I'm sure that people won't start we've been doing it the opposite direction.
But isn't the D for distance?
For shared conception distance.
Small distance good.
But here we took the winning average between the models. So we took account for the fact that smaller.
I see.
Obviously,
good.
Cool. So we suggest you update the standard protocol for evaluating text-to-image models by taking prompts from Pick-a-Pic rather than MS Coco captions, and to use Pick-Score rather than FID. And
can you also use Pick-Score to evaluate, let's say, GANs without prompts?
So that's a very interesting question, and I'd love for follow-up work to see how well Pick-Score generalizes.
Nice picture.
Okay. I'd love to see it. I don't have a definitive answer for that. So the next thing that we try to do is we try to think of the simplest way to improve text-to-image generation with Pick-Score. So what we did, very naively, we just took the vanilla model, generated a bunch of images, scored them,
and
returned the best. And we can see both qualitatively and quantitatively that Pick-Score usually selects a better image, both than the original model and more than a statics predictor or a clip. And finally, I think that it can be interesting to put some context before, because these conferences happen several months after we publish. So since then, both the scoring function and the dataset was pretty widely adopted. And two notable works that I really loved and like wanted to like highlight a bit in my poster was making PickScore a metric for text-guided video editing benchmark to measure video quality, and very interesting work by Wallace et al. Improved SDXL by extending DPO for diffusion models and doing it on Pick-a-Pic datasets.
I see. So
And they were able to improve SDXL.
And I'm gonna guess this was SDXL or some stable diffusion already.
It was lots of different models. We wanted to make it more diverse.
Cool.
Awesome.
So it is actually, the whole loop is a bit like reinforcement learning from human feedback, right? Like ultimately, okay.
Yeah,
very cool.
Definitely,
very cool.
yeah. And I hope that people will continue like to look at the stuff, continue to open source, and
Awesome. Well, thank you very much.
Yeah, nice meeting you in person.
Nice meeting you. I've not even read the title, so you have to introduce me.
So this paper is about image geolocalization. So image geolocalization means given an image, we want to identify the GPS coordinates of it. The GPS coordinates means the latitude, longitude of it, right? So suppose you are given a particular image, you want to know which location this image has been taken from.
Yeah.
The problem here is this image can be taken in the any world, any part of the whole world.
Yeah.
So you have to match it throughout the world and identify the location of it.
What kind of data do you have available? Street view?
It's Street view.
Okay.
Yeah. So that's why
this is like GeoGuessr.
Kind of.
Okay. Yeah.
So it's like a worldwide image geolocalization, right? You want to do at the world level, like global level. So existing approaches, they do it via classification-based approach. So they divide the whole Earth into grids, and then they classify which grid the particular image belongs to. But the problem is the grid center location is the GPS coordinate. Always they say that. But if the image deviates from that, then localization creeps in. And also number of classes depends on the how many classes you are taking. So we avoid those approaches. We take a retrieval-based approach. And there are also some approaches which are image-to-image retrieval approach. But we don't do image-to-image because you need to have a gallery of the whole world, whole Earth, which is not possible to have. So we take image to GPS retrieval. So what we do is we pass the image to image encoder, clip-based image encoder. And there's a gallery of GPS coordinates. We pass it to location encoder to get location features. And then we do contrastive learning. So now the challenge is these are 2D coordinates. We want to get a high dimension representation, right? For that, this is our location encoder, right? So how to do that? So let's say this is the GPS coordinates. We first pass it to equal Earth projection. So normal GPS coordinates, traditional lat long, have inherent distortions. Some countries are overrepresented, some countries are less represented near the polar regions and so on and so forth. So we do a better representation, equal representation. Then after this again 2D only. So then what we do is we pass it to random Fourier features. Random Fourier features is a sinusoidal position encoding technique. So we take a matrix R, sample from some Gaussian, then multiply it and then have sines and cosines of it. But here, if you take a particular sigma, it is capturing a particular type of frequencies. So we want to capture frequencies spanning from both coarser to fine grain, because we want to perform well on both coarse, fine grain, and also coarse and fine grain both. This is fine grain, this is coarser. So we take a series of sigmas, pass it to dedicated MLPs, combine them by simple addition operation. That is our feature.
So you have a multi-frequency, like all the frequencies in
combined together.
It's like a random up projection, but in different frequency domains. So
now these are performance on these different data sets. And across different threshold metrics, our performance is better. And also the good thing is, if you have a text as a query, you can replace this through a text, replace the image encoder through text encoder. This is already pre-trained. So you don't have to train it again. This is also implicitly aligned. So you can get a similarity scores for all the GPS coordinates. You can get a similarity map kind of a thing. Right? So if the text query is desert, let's say with a generic query, it is able to localize throughout the world. And also it is a specific city or specific landmarks is able to geolocalize it. And lastly, the thing is the location encoder can be used for other tasks also. If you have a task like classification, you can also use our location features to combine the image features and get better performance.
Very cool, very cool. Would it be, I'm just guessing, but Street View is sampled very differently throughout the world, right? So here you're kind of trying to get the area, relative to the size. But could you also have a transformation that just transforms so that where street view pictures are more often, you get like higher density of grid points?
Right.
Would you expect that to help?
That helps actually.
Yeah.
So our gallery, during gallery construction, we try to use the training set knowledge. Training set data has been prepared via more samples from those regions where humans reside. Yeah. And less samples from those regions which are not important, like oceans or deserts. Yeah. So that prior knowledge in the training set, we utilize that one. Okay. So we randomly sample the train set to create our gallery. Yeah. That helps better than randomly sampling the whole Earth.
Yeah. Okay. Very cool. Very cool. And I wondered like what you can use this stuff for. Will this mostly work for stuff that's also represented in the images, or I don't know, like what here, if you enter, for example, I don't know, Christianity, would sort of the Christian world light up, or is it only things that kind of represented in street view images?
So it might be possible. What happens to that is that whatever features are left in embedding a space are the ones that are useful for geo-localization. Yeah. Right. So, for example, if you have the query Christianity, given there are so many places that are like Christian, it wouldn't be like a feature that to make a place recognizable. So maybe that dimension will be collapsed when passing through the features, like different linear layers.
And do you have the same model for all of these granularities, or do you train like different models?
We have the same model for all the granularities.
And you just rely on sort of the different embedding sizes you have there? Yeah. Oh, very cool, very cool. Have you competed in GeoGuessr with this?
We would like to actually, but we haven't tried.
Yeah, we haven't tried yet.
There's there's a couple of these YouTubers, right?
Yeah, like Rainbow and.
Yeah, exactly. That you have to call them and be like, hey, we have a new best AI. They'd be pumped.
Yeah, that would be cool to try. Yeah.
All right, thank you very much.
Thank you.
A pleasure. Thank you. Very cool work.
The videos, explanations are too good. Very nice.
Thank you. Thank you very much. Is it okay if I recorded them?
Yeah.
Okay. What do my text-guided image classifiers have to do with hardware?
So basically what we're trying to do is we're trying to use those text features that are generated from the texts and then trying to initialize the last layer by instead of like doing a random initialization for the last layer that based on how we do previously. We wanted to use those class descriptions or those text descriptions and then pre-train the last layer, and then now you can plug in any machine learning architecture that you have, ResNet, AlexNet, or even your own classification architecture with it, and then use it to train it. So what it does is when you do those like text descriptions and then like initialize the last layer, it makes the model more confident enough for it to actually be resilient when bit flip errors or as manufacturing defects actually happen on the hardware.
Okay, so the original problem is a hardware defect.
Exactly.
In what exactly? In the image sensor or in the...
The hardware defect is actually like, we're talking about the deployment. When the models are trained and then deployed on the hardware. Yeah.
When the hardware could be
affected by like voltage drops, manufacturing defect and so on. And then when that happens, silent data corruptions actually happen on the model, which makes it doesn't crash the system, rather it makes the model do like wrong inferences instead of the right ones.
Okay, so if I imagine I train my model for myself driving car, I deploy it in the car, the model gets corrupted, and then my car just kind of gets worse.
Yeah, it might like speed up when it shouldn't, or it might actually like detect something incorrect.
Okay, so that's this part right here. This part might get worse.
Exactly.
Okay, and then...
So like this is so after inputting it, this is your final model. Like this is your final architecture. So if you didn't have, when this one gets corrupted, now it will be doing wrong inferences instead of the right one. Yeah.
And so what's your method exactly doing to counter that?
Basically, like this one, it gives us all the features, and what happens here is that we actually have, instead of like initializing the last layer values randomly, it gives it the initial setup, or a smart way to give it the initial setup. And whenever you're doing the training, it will be more confident on whatever inferences that is going to make.
Okay, so this is, let's say, an image classifier.
Yep.
And you initialize this here somehow.
Yep.
To make it more robust.
Exactly.
What does this have to do with text input exactly?
Okay, so basically what we do is, let's say you have like 10 classes.
Yeah.
So currently we use GPT-3.
Yeah.
So we asked GPT-3 multiple questions for each class, and then GPT-3 gave us multiple descriptions.
Okay.
So we took those descriptions and then we gave it to CLIP to give us the embeddings.
Yeah.
And then those embeddings, now we have multiple descriptions with embeddings, so we averaged that one. So now we actually have a more robust information about that image. And then after averaging it, we use that to initialize the projection layer.
So you just get somehow some sort of a class embedding that you get out of all of these texts about the different classes that you get from sort of the CLIP text encoder.
Yeah.
That is very smart.
Thank you.
And but why do you think it helps? Again, so if I corrupt something here, right, then you're saying this is more robust now. Why do you think that is?
Yeah, well, the thing is, like, when bit flips, let's say if a bit flip happens like in the beginning layer or in between, there's a probability that since convolutional neural networks, when it's doing like when it's going through, there's a probability that of it being corrected through the process by ReLU or other activation functions. But if a bit flip happens on the final layer, it's actually like affecting the final decision of the model.
Yeah.
So the best way to actually increase the resilience is, what if we could actually focus on the most vulnerable layer instead of the whole?
And if so, sometimes people do checksums and things like this. I think hardware GPUs already have sort of error correction built in.
Yeah.
Doesn't that also help, or is what you're doing kind of complementary to that?
Yeah, well, like the existing, like the state of the art or the existing one, like the parity checks or error correcting codes mainly focus on the storage, but it doesn't cover the computational part.
Okay.
And like let's say, for example, Tesla introduces full modular hardware redundancy, on which they introduce redundancy. But with that, what comes is that hardware is actually using more power. And since it has redundancy, it's actually like being latent and taking more time in making the decision. Of course, it's not visible, but in the computer science environment, the small latency actually matters. So what we're providing is, instead of providing a power-consuming and then more redundant solution, what if we could actually train the model thinking about the hardware resiliency?
I see. Very cool. And then you test that. Do you actually trash your hardware, or do you just sort of artificially corrupt some stuff?
Yeah, we have a framework called GoldenEye. So GoldenEye actually simulates a real-time hardware environment on which we use GoldenEye to do the error injections on both the baseline and then our proposed model. And then after doing that, we check we have two options on which we measure. That's delta loss and top to diff.
Yeah.
So delta loss gives us the overall information on what's happening when wrong and right inferences are being made, and top to diff shows us how confident the model is when it's actually making the classifications. And then by using that, we see how the model is actually resilient based on the error injections we did on it.
Very cool. And is it more resilient?
It is.
Okay, good.
And like surprisingly, like we achieve actually 5.5 times average resiliency improvement with up to 14 times improvement, and then with a minimum drop of 0.3% on inaccuracy. And then that accuracy drop is actually mainly on the noise, not like on the noise image that are already highly likely to be misclassified.
Very cool. So you're saying that where these things matter most, these flips and so on, is in the images that are already kind of shaky? Not sure?
Exactly. So what we're doing here is actually increasing the model's confidence in making those decisions.
Okay. So it actually increases the model confidence across the board, but it most matters in the ones that are on the edge and on the border. So
yeah, that's very, very cool.
Yeah.
Thanks a lot for the explanation.
Thank you so much. Thank you.
Thank you. Have a nice day.
Thank you so much. Take care.